So thank you everyone for attending this Galaxy Colloquium. Today's speaker is Xichen. He's our own Galaxy PhD student, but he just defended his thesis successfully, so we can maybe call him Dr. Xi. Xichen graduated from University of Illinois Urbana-Champaign. He actually worked there as an undergraduate researcher with me, and he was a direct PhD student, and then he moved to Caltech. After his PhD, he's supposed to start at Waymo as one of the leading self-driving car software engineer there. So Xichen, now is all yours.
All right, thank you, Sindro, for the introduction. The topic I'm presenting today is on the intelligent control for fixed-wing eVTOL aircraft. eVTOL stands for electrical vertical takeoff and landing. Before we dive in, first, let me give you some motivation and backgrounds on the concept here. In 2016, excuse me, Uber published a white paper on the concept of urban air mobility, which is to reduce travel time in metropolitan areas. As you can see on the graphics here, traveling from San Francisco and San Jose takes around 2 hours by train, 1 hour and 40 minutes by car, but just 50 minutes if you're traveling by air on a VTOL aircraft. As for that, we need something that can take off and landing vertically at the same time covering longer distance, approximately around 50 miles, in order for inter or intra-city travels to be usable. And it's natural to have combining fixed wing aircraft and also electrical multi-rotors, because now you can have both efficient longer range flight at the same time using multi-rotors to take off and land vertically. But there will be challenges stem from using this kind of hybrid concept, because now interactions between different rotors and wings will become complex and hard to model in most cases. And furthermore, the disturbances from the environment could be also complex to model because we're operating very cluttered urban settings. So that means the autonomy on board the vehicle will require an enhanced level of precision, safety, and also intelligence. Here's a montage of different commercial solutions that have been proposed and built prototyped to date. You can see most of them having this main wing and also more than 8 vertical rotors as this hybrid here. In the middle of this montage is one of our own CAS autonomous flying ambulance project. Here we show a render of one of our design. I eventually built those designs into functional prototypes to test some of the theories that we do for the autonomy aspect. So this work is roughly divided into 2 parts. During the first part, we'll cover various aspects of fixed-wing eVTOLs, talking about why their benefits, where their benefits coming from, how to design control system, how to improve certain design aspects. And in the second part, we'll discuss more novel method in learning and also in actuation and compensations. So let's first lay some foundations and try to understand what is the advantage of having a fixed wing eVTOL here. We can use disk momentum theory to understand for a rotor in the ascending, hover, and descending flight, how much power is required for a certain area of the rotors generating a certain amount of thrust. By balancing the mass, momentum, energy equations, we can eventually get a relationship calculating the induced power to satisfy those thrust generation needs. Similarly, we can do it for forward flight, except the case is more complex case here, because now your flow can be coming at an angle of attack with respect to the rotor plane. But nevertheless, we can get similar relationship by using the thrust generated and also induced velocity from the rotor plane. Apart from induced power, there's also rotor profile power, which is the power you need to rotate a rotor around through the air. And also the amount of power you have to overcome by generating certain forces on the wing as well. For battery or electric vehicles, we have a battery model that determines how much time the battery would discharge given its capacity and the power load. Now, putting everything together, what we try to understand is how much power is needed for different flight modes. It's a simple case for hover flight. all your vertical rotors would be balancing out the weight for the aircraft. Moving on to a VTOL forward flight, now your rotors, you'll be tilting the vehicle in the direction of flight. At the same time, the rotors will be satisfying both the weight and also the drag that's caused by having your aircraft moving through the air. At the same time, some downward lift may be caused by a downward angle you have on your wing surfaces. For more mixed flight modes, your wing will be generating most of the lift to counterbalance the weight, with any additional lift can be compensated by the vertical rotors. And in this case, you'll be flying flat and your back cruise rotors can be used for compensating for drag. And putting all of those together and use those tools, we can analyze designs such as the AFA 2.0 concept here. And here we show this from sketches to render to actual prototypes. And applying those equations on this particular fifth scale prototype shown in the lower right corner here, we can understand how much power and the composition of power during different flight modes with a range of different flight speed. So on the left here showing during a VTOL only mode, as you can see, most of the power comes from the rotor power. They dominate over the aerodynamic powers, except at higher velocity, your power basically increases significantly. On the other hand, for a fixed wing flight mode, at higher velocity, you're more efficient as in using less amount of power here. And also, in this case, the rotor power doesn't dominate at higher speed, rather the aerodynamic power will dominate. And we can compare them side by side and also incorporate the electric range equation, the battery capacity equations to calculate the amount of time your aircraft can stay in the air, or we call it the endurance, and the distance your aircraft can travel, or the range of it. So showing on the left here, showing the graph on the left here is showing the power required and also the endurance. On the right is a pseudo thrust, which is power divided by forward velocity, and the range. As you can see, even in this small fifth scale model, we can achieve 2 times improvements in both range and endurance. And we can expect this to also hold for larger scale aircrafts. So this is the main reason, using first principles, using physics, we can understand what is the need for a fixed wing VTOL hybrid.
Xichen, sorry, did you define what AFA stands for?
Yeah, we did.
Okay.
Autonomous flying ambulance that we have at Caltech. So having the aircraft now, how do we design a control system for it? So we already know for a VTOL multi-rotor flight, your aircraft will be tilting in the direction of flight for the thrust generating by the vertical rotors. For a cruise flight, you would have your wing to generate the lift, at the same time the back rotors to generate thrust flying forward. Our hybrid flight will have something in between. Maybe you have some flight at lower flight speed, you're flying like a VTOL. At higher flight speed, you transition into a fixed wing aircraft. So there were a lot of works before that. I'm trying to understand how to transition from one to the other. Usually they would require, we have 2 controllers for each flight mode and try to stitch and switch different controllers together. If it happens to be a tilt angles, we can schedule the tilting of such angles and then do their controls accordingly. If you have a good models of the entire craft, you can try to optimize it offline and use that trajectory for the online transition. Excuse me. Or if you have enough computation power, you can actually solve everything online. Although in practice, it's not very likely due to the complex model and the computation requirements, computation hardware that's typically smaller on these flying vehicles. So in our case, we propose a framework that's based on a feedback control design, where we use the same position and velocity position and attitude controllers throughout different flight modes, and just to tie everything together using force allocation and control allocation blocks. So introduced here is a very simple 6 degree of freedom rigid body dynamics model for flying aircraft. We decompose the body forces and torques into the thrustor components with a subscript T, and the aerodynamic components with a subscript A. Now, thrustor components we can usually use a model that's linear in the square of rotation speed to calculate the thrust and torque generated for each thrusters. And we can combine them based on their configuration, a linear mapping from individual thruster forces to the total thruster force and torques. For aerodynamics, we can use non-dimensional coefficients, try to represent the different aerodynamic aspects by calculating the angle of attack and angle of side slip, which is the relative angles from the of the wind onto the airplane. We can use a blended method to blend two blend a linear aerodynamic model with a nonlinear one, because during the linear region you have this monocyclic rise of coefficient respect to some angles, and you have a star region. And during the full range from -180 to 180 degrees, you will see a more sinusoidal or some sort of trigonometric relationship. As you can see, this model, we can tune it to agree pretty well with experimental data tested on wings and airfoils. Now, our architecture consists of several parts. First, we use the force and torques as control input to design position and attitude control. Now, it depends on the force that's being commanded. We have to allocate the force by determining the attitude, RD, which will determine how much aerodynamic force we can generate, and also thruster force, FT, the force from all the thrusters we can generate. And then the control allocation will determine individual thruster forces and also aerodynamic surface deflection, if there is any. Using force and torque design controllers make the problem very easy. Here we just present a simple globally exponential position control by using the force as the input. We can prove this has nice properties given that your force commanded can be satisfied within some bound. And similarly, this is an SO3 almost global attitude tracking controllers. That is, as before, you can achieve globally exponential stability, given that your torque requirement can be satisfied within some bound. Now the question is, how do we generate those force and torques? So for force allocation, the first step is determining desired attitude. For low speed, all we have to do is to ignore the aerodynamic forces and try to align the rotor in the direction of flight, just as a multi-rotor would fly. For higher speed, you will have to prioritize wing lift by calculating the desired angle of attack, and then use try to get a rotation matrix from our current frame to the desired frame. And then we can, for the looking at the current state of the aircraft, we can subtract the amount of aerodynamic force that we estimate the aircraft is generating, subtract that from our desired force, and then let the rest to be satisfied by the thruster forces. But oftentimes it's not possible to satisfy all kinds of thruster forces, so we apply a mask to get to it. For example, in this case, only Z or body Z and body X force are achievable, where Y force are usually non-achievable. Now the next problem is control allocation. The problem is, given the thruster and torque, what is the individual commands were given to the rotors? We know the mapping is a linear mapping. W equals BT. W is the combined force and torque. Here we call it the wrench. Usually we have a feasible control space, the maximum amount of thrust each thruster can generate. And that typically looks like a hypercube inside some high dimensional space. And by applying a linear mapping to it, we can have a polytope that's in R6, for example. Now we call this feasible control space, and this part is the attainable range space. So the problem would be, graphically, given something inside the attainable range space, what is the control inside the feasible control space? So it can be formulated as a QP to minimize the effort of control at the same time, satisfying all the need and the feasibilities. So obviously you can solve that control problem, solve that optimization problem but it would be actually slower than needed because control allocation happens on the lowest level of the entire hierarchical architecture and require the fastest update rate. So in practice, often we will use a simple linear mapping. For example, a right pseudo inverse. The right pseudo inverse is the optimal solution to the original problem if we don't have an inequality constraint. However, simply applying this right pseudo inverse onto this polytope attainable space here, you wouldn't get the feasible space. You would get some space that could lie outside the feasible space, meaning you will have saturated control inputs. So how do we handle it? So one solution we propose is to have a offline optimized inverse mapping BT prime. So we can minimize this with some problem setup. Try to minimize the frequency more is to minimize the potential efforts of control. We also want each rotor to have similar amount of thrust during allocation, so their deviations are small. And also we can fit a apply range space, something like a hyperrectangle inside this polytope, such that we can show in simulation by applying this optimized inverse, the space you recovered will be always inside the feasible range, feasible control space, so that we don't have we avoid the saturation problems. Or if you still will have saturation, we can also do a recursive control allocation. It's by eliminate saturated control signals one by one recursively. Now here's a simulation by randomly sampling 100,000 different range inside a attainable range space and look at how the allocation will work using different methods. So the PN is the pseudo inverse. The quadratic program is solving an optimal optimization, and the RCA is the recursive control allocations. As you can see, the pseudo inverse has a baseline computation time of 1, but you would have to saturate some controls if you're not using the offline method to optimize that inverse map. On the other hand, optimization will have 0 saturation, but will have 3 order of magnitude higher computation need. RCA, however, would achieve 0% saturation at very minimum addition to the computation cost. Now, putting the proposed architecture through a simulation environment, when we're given a very simple velocity profile, simply telling the aircraft to go upwards for 5 seconds at the speed of 5 meters per second and go forward at the speed of 15 meters per second, the aircraft can exhibit a very natural transition trajectory. And noting that transition trajectory wasn't designed before, right? Rather it's exhibited by this architecture intrinsically. So you can see in the beginning, the allocation tells the aircraft you have to be flat, 0 pitch going upwards. At some point, pitch downwards to gain some speed, and when we have enough speed, go back to around 0 pitch again for fast forward flight. All of this achieved intrinsically within the architecture. We can also apply this to a real environment by putting in front of fan array wind tunnel, and that can generate uniform flow up to about 8 meters per second in this case. So we first have the pilot input some 3D attitude and 2D force commands. And then we can achieve some reasonable results by having decent attitude tracking, flying in front of the wind. But the problem here is the pilot will have to input those manually, and he would have it would be challenging for him to hold the position at the same time, because we have to assume the wind is uniform in our case. So how do we improve this real-time unsteadiness that can occur from the flow? So what we propose instead further is a physics-based adaptive method. And there were a lot of adaptive control literatures on, for example, linear parameters models, or using composite adaptation by incorporating both tracking and prediction errors. For flight control, there are works estimating angle of attack and angle of side slips online, but mostly for estimation purpose, not for control. But for flight control, we can do, there has been work done on adapting aerodynamic coefficient or neural network parameters. So in our case, we know force allocation is the key to achieve very accurate precision tracking. And the key to that is to have an accurate force estimation. So in this part, we actually use a more simpler vehicle that has multi-rotors and fixed wing and forward rotors. At the same time, it's incorporating a novel sensor that can get more information out of the flow. Using the same rotor model, but augmented with the psi force. So we add the psi force of the rotor that could become significant during forward flight. And we use the same linear and quadratic aerodynamic models with respect to lift and drag before. We have this novel sensors that use differential pressures to back out a incidence velocity onto the main wing. I'll combine them together. We can actually write the body force as a linear combination of parameter vectors and also a basis function matrix. With this form, we can design a composite adaptation scheme that's adapting both the tracking error at the same time the prediction error. The prediction error is simply the difference between the measured acceleration after the filtering and also the predicted acceleration after the filtering. And we can further augment it via a recursive least square method with the exponential forgetting. So now the adaptation scheme online will be as if it's solving a least square problem with the exponential decaying window. So we test this in front of fan array wind tunnel in a motion capture environment for feedback position control. So the first showcase we'll have here is as the airspeed ramps up, we'll see the aircraft align itself with the flow in order to satisfy the additional forces from the aerodynamics of the wing. As you can see, as the speed ramp up, your angle of attack and angle of side slip initially unregulated, eventually become regulated towards some angle determined by the force allocation. And the aircraft pitch up slightly to generate the amount of thrust needed, generate the amount of lift needed from the wing. Now in the second showcase, we will tilt the entire wind tunnel from 0 to 9 degrees and back to 0, while keeping the wind speed relatively constant. So in this case, the wind direction changes. As you can see internally, the allocation tells the angle of attack and angle of side slip to stay relatively constant, but we have a varying pitch from as the aircraft is tilting into the wind and then back flat again to satisfy to fly according to what the wind direction is demanding. So we have this simple force controller as before. We augmented with composite adaptive controller. We would like to compare it with a baseline PD and PID controller where the parameters are fixed. Now those fixed parameters are obtained through wind tunnel testings, and they're fairly accurate for steady state purposes. But as we'll see for transient effect, they don't perform so well. In this experimental case we'll show next, we'll be ramping the fan array profile from 0 to 30 to 50 to 70%, and then suddenly shut it off. That would roughly correspond to 4, 6.5, and 9 meter per second wind. Now, if we first look at, let's first look at PD versus PID controls. The upper plot is PD, the bottom is PID. It flies pretty steadily, except every time when the wind ramps up, you see a sudden drift from its holded position. Now the integral control comes back over time, given its integrated power in that I term. But in the end, with a sudden drop off of velocity, you will set a huge overshoot from the PID. Now we can see when we compare PID against a composite adaptive controller. See the upper graph is the composite adaptive control. Now here is a constant gain. So now every time the transient effect from sudden ramp up or ramp down of wind is minimized. Basically, there's no difference visually from the precision tracking performance when the wind changes. And in the end, during the sudden shut off, your overshoots is also minimized. The additional comparison we did is on comparing the constant gain versus when the gain is updated in the recursive least square fashion. We expect least square to have a better prediction and tracking performance, but in our case, it actually did not improve the performance further. And in some cases, you can see the the constant gain outperforms the RLs, the recursive least square. We plot everything together, as you can also see in this set of graph here, to further just to summarize what we have shown in the videos from the improvements we have over baselines on the adaptive controllers, and also the prediction performance by using adaptive control, because now you can predicting the forces, the magnitude of forces as well. So next we present a method for eVTOL designs that can make the rotor configurations more tolerant towards rotor failures. So we have the same dynamics as before, except now we focus mostly on the rotor force and torques. And we will test and analyze based on a simple rotorcraft. This is the AFA 1.0 prototype shown here with the rotor defined on the graphics here. The prior work on fault tolerant control usually focus on having a backup controller whenever a fault is detected, at the cost of reducing attitude authorities. For example, a hexacopter with 6 rotors would lose yaw control completely in event of losing a rotor, but you can recover some of the authorities by having rotor tilting out of the plane. So in this work, we will focus on the design aspect of it, is how to get a configuration that's most optimum for different failure cases. So first, we define a static cover as eventually a problem of just reaching 0 attitude, because through position and force control, the convergence of attitude will eventually become 0 in a static cover. So given the definition of null controllability as the system's ability to return to a 0 state given feasible control inputs, we find that for the attitude subsystem, for it to be null controllable, meaning for it to become stabilized back to 0 attitude, is required that the thrust, the torque, 0 torque, is in the interior of the moment space. So what does it mean? It means that basically the origin, when you have a moment space in R3, your origin has to be on the inside of it. So it cannot be on the boundary or on the outside. We define this moment space by using the maximum thrust and the rotor configurations. And we know this moment space could be determined by some design parameters, such as rotor locations or orientations. We define a quality measure of controllability by putting a cuboid that's fixed center at origin and the maximum size of it inside this moment space. And we define its scale as kappa bar, and that's our metric. So basically, bigger this box is, the bigger the controllability of the aircraft in various cases are. Now, the fault tolerant design procedure is listed as follows. We first have a set of all possible failures and also parameter space. And for each of those elements, each failure case, each design, we can optimize this convex problem to solve for that metric kappa bar we just discussed. And then we optimize for the worst case behavior. We maximize this metric for the worst case failure case, worst case rotor failures. So among all failures, what is the minimum, and I'll try to maximize the minimum. So here, example of that AFA 1.0, by designing the rotor tilt angles symmetrically, bounded from 0 to 20 degrees. And in this case, it turns out we can have an optimum design parameter of 19 degrees and 13 degrees respectively. And comparing to the baseline of only non-tilting of 0 degrees, we can see the metric, the controllability metric, improves on all rotor failure cases. And especially in cases such as failing rotors 3 and 7, the baseline case will have that origin on the boundary of the moment, meaning it cannot generate the uncoupled moments in different axes, whereas we can recover some controllability by having the optimal design. As in, you can see the origin is on the interior here. In another case, when fitting rotors 1 and 8, we can see a significant increase in the moments in the metric by fitting this cuboid inside this moment space. Now, for the same failure case 1-8, we do it failure in flight and compare the performance of control by perturbing roll, pitch, and yaw axes separately. So what you want to see here is for baseline, the roll pitch perturbations basically have no effects on the overall performance as the position tracking, position holding is relatively well, except when you perturb yaw, during the negative yaw case, you have issues tracking the desired trajectory because the loss of authority in the moment space. When you have an optimum design, now we recover some control authorities, so this does not happen anymore. All right, so before we move to the next part, are there any questions? Okay. So now let's talk about how do we improve the control intelligence by having, for example, learning-based method, in particular, a neural network-based method. So far we have this body force and body torques that we know we have to model, and we model it via the thruster forces or nonlinear or linear aerodynamic forces. And overall, we know the thruster force, we're pretty confident because they end up agreeing with the experiments very well. And aerodynamic maybe not so much. And it's natural for us to think about a data-driven approach for approximating FA and tau A using deep neural networks. And given a lot of research on deep neural networks, there also been a lot of combined new DNN and control work as well. People have been using deep neural networks to do system IDs on, for example, helicopter dynamics, using neural network to generate trajectories and feed it onto the downstream controller. Reinforced learning with continuous actions are particularly related to control, for control applications. Also, we could learn the inverse dynamics through the DNN and apply controller to it, or learning Lyapunov functions. And in our case, we'll present two approach. The one is designing a feedback controller when partially your dynamics is represented by DNN. And also when your full dynamics is represented by DNN, how would you design controllers and observers and how to train them respectively. So given an L hidden layer V4 network, where W is the matrix of the weight parameters of each layer, and the phi act is a ReLU activation function. It turns out we can regulate the Lipschitz of this entire network through some determined constant lambda by applying spectral normalization on each weight layers. And for control, we know we want to satisfy the desired control as before, desired force as from the position controller as before. And in the case of multi-rotor, it's basically having the thrust from rotors equal to the amount of desired force subtracted by the aerodynamic contributions. So we equate that into solving the control allocation problem again, except now our control input shows up on both sides of the equation, because adding this additional DNN making the entire problem non-affine control. So what we propose is using a fixed point iterative method by feeding the control input from the last time step into the neural network and subtract it from the desired force, and then do inverse mapping on top of it. And turns out, in order for this to converge and work, the Lipschitz of the network multiplying by the singular value of this inverse matrix has to be less than 1, meaning the entire mapping has to be a contraction. So with some assumptions on the projection trajectory are smooth and bounded, our controller updates are fast enough for some against some scale factor of our error, and also our learning are effective in the sense that it has some very bounded learning errors. We can actually prove the entire closed loop system under this controller is globally is exponentially stable, given the gains, the learning error bounds, and also the Lipschitz of our network. So to show the results, we apply the method on a quad-rotor drone, the Intel Aero drone here, by doing some data collection first, and then do some offline batch training, and then deploy the controller online. So the first thing we want to show here is that applying spectral normalization to DNNs actually gives better generalization for the network. Now on the upper graph is the vertical forces plotted against the vertical velocity with vertical height. So on new domains, which is a domain we haven't collected any training data, the spectrally normalized DNN show better smoothness functional predictions, whereas the non-spectral normalized ones actually have this large deviant given the data that hasn't been seen before. And in practice, it corresponds to a sudden failure of the controller at these data points because it hasn't predicted very large and erroneous forces. On the bottom graph is when we train the data when the vehicles flying across tables, we can see the spectrally normalized network has a very clear table boundaries, whereas the unspectral normalized ones doesn't have it and also have the large deviant somewhere in the data space. Now for closed loop control performance, we can outperform baselines, for example, in landing by having a very smooth and zero speed touchdown on the ground, where the baseline can't even touch the ground without integrative term or because it's not considering the actual additional cushioning effect. Similarly, for vehicles flying across tables, our controllers can get as close to the table as they can, and the baseline will have the problem accommodating the additional cushioning force from the table, also dropping off when it reaches the cliff. So in general, the method applied on the flight control can also be done on any fully actuated FINA control baseline dynamic system, augmented by a general DNN residual dynamics. That's a function of state and control. So we can apply the same principle and improve the same stability using that on that controller. The controller is basically the inverse, and then feedback in the control input from the last time step. Now this is all good except there's a harsh constraint on the approximator on this residual, and that is the Lipschitz of this network has to be less than 1 over the Lipschitz of the inverse of that matrix. That's already known. When this is already known, that means this is the Lipschitz is fixed. And in practice, there could be a problem in the sense that when you don't know this additional forces and when it becomes too large or non-smooth, this condition wouldn't hold and you wouldn't get a good controller from that. So in general, we would potentially represent our entire dynamic as a deep neural network. Then we want to design a controller based on that. But the problem with non-affine controls, how do we do it? Or theoretically, we can do it by just solving this equation. We already have the dynamics learned somehow. We equate it to some closed loop behavior we want to achieve. If we can solve it, we have a controller. But instead, we propose to represent our controller with another neural network parameterized by theta c. Now, how do we train both networks? So we first have to do some data collection. And given the method we're going to propose is off policy, this collection can be done by some experts, or can even use the same controller untrained controller we have to do some random exploration. And during the first stage, we will learn the dynamics by looking at the state, control, and state derivative pairs, and doing a supervised learning to figure out what is the transition function. So this stage will be learning the parameter theta f for the dynamics network. And the next stage, using the dynamics network that's already learned, we fix that parameter theta f, and we feed it into a Lyapunov derivative estimator. So this is propagating one step forward using our dynamics that's already learned and using our controller that's being learned. So we optimize this loss function. This loss function is penalizing any negative terms of this expression here. So when this when v dot plus alpha v becomes negative, penalizing any positive terms. When this term becomes negative, it's considered the system exponentially stable. When it's not, there could be some issues to it. That's why we penalize. So overall, through this, minimizing this loss function, we can train the network parameter for the controller theta c. But there are often cases that what we really have is only output Y instead of the state X. The state X dimension could be unknown. For example, you could be given a picture of the drone or some robots, and the state that governs its dynamics could be more than what you believe it is. On a drone, position, velocity, and attitude may be sufficient, but when encountering wind, you could be introducing more states as needed. So what we really want is to have additional approximations that somehow transform between a known observation that we already have to potentially more states that we can incorporate into the dynamics. So we do that through two additional networks. One is called the observation model network, parameterized by theta H, and the observer network, parameterized by theta O. So these have a general observation model and observer form, as in general dynamics models. When we convert it into a discrete sense, it becomes recurrent network structures. So let me explain this in detail here. So every time step, you're given the observation, the current observations. You're also given the prior estimate of your observations and also the prior estimate of your states. Now your observer network will take those in and output a posterior estimate of the states. Feed that into the controller together with the current observation, the desired observation, and the derivative of the desired observation. And the controller would give out a control input U, together with the posterior estimate of states, goes into the dynamics that we already learned, propagate forward to get the prior estimate of state for the next time step. At the same time, we'll go into the observation network to give the estimate of observation for the next time step. And we'll do this recurrently over time. So how do we learn it? We learn it using similar methods as before. The data collection is also off policy, so it can be through some expert controllers or some random controllers. But if we're to apply this online, we'll do this recurrent structure as before. And when we're doing learning, instead of doing sampling randomly from the data, we actually have to have a sequential trajectory, because our formulation RNN will have to train on a trajectory. And during the dynamics learning stage, we'll be learning learning dynamics by optimizing the dynamics network, the observation model network, and also the observer network. And in the control learning stage, we'll fix these three networks and only learn the controller using a similar approach as we discussed earlier, except now it's in a discrete sense. So these overall framework can, and in principle, learn a more general form of dynamics when it's all represented by DNN. So next we'll briefly discuss how do we compensate for delays in actuation systems. So here's the example of such problems exist in practice. So when I was first implementing our nonlinear controllers on some drones, such as the quad rotor and a fixed wing eVTOL here, I noticed that when I compare it against the PID controller, the PID has an additional D term on the derivative of the error here. That doesn't exist in the nonlinear attitude control. And the first intuition I have is maybe the only resemblance is in the feed-forward term on the inertia would have some similar effects as the KD term on the from the PID. So maybe you have to tune the inertia, and that's what I did. And it turns out it worked pretty good for these bigger drones. But when I transform the smaller drones, tuning inertia no longer works, except when you have to tune it 10 times larger than its original intended value. And further investigated, noticing that the inertia of smaller drones is several orders of magnitude smaller than the bigger ones. While the delays on the motors, however, are on the similar time scales. So then we focus on the problem must be coming from the delays, and how do we compensate for it? So delay compensation has a long line of research before. People have been using PID or PIPD controller on linear systems, or that there has been vast work on predictive control by continuously integrating states for future predictions. But they would require partial differential equation or functional differential equation analysis. In our case, we'll still propose a predictive controller, but we will focus on when the integration is numerical instead of continuous. And also our system updates in a sample-based or discrete fashion. Also some mathematical setup. Skips through this, but the basic gist is there's the original system of or undelayed. We consider, for example, we already designed a controller for our quad rotors, but we didn't consider the delay. We know there's a controller we already designed, ADA bar, that's designed for the undelayed system that's already making the undelayed system exponentially stable. And then we incorporate a delay model. So we know in practice, at every time sample TI, we will be sampling some states. We'll be computing a control signal U using this time delta C. We'll finish computing, we'll send over to the actuator with time delta S, the system delay. Now at TI prime, the signal reaches the actuator, and the actuator has to evolve according to a first order delay dynamics that we propose. So the overall model we use here is a sample-based first order plus dead time model. So the first step we do is accommodate for this first order delay. And it becomes very simple, just simply having this baseline controller we already designed before, and taking a derivative of it and multiplying by this first order time constant. This simple addition can accommodate for first order delay. Is converged as fast as this time constant allows. But if you want to augment it with an observer, then you can actually make it converge faster than the first order time constant, while paying the price of having observer error in your system. So we call this general first order compensator ADA bar double prime. And then we want to incorporate this discrete delay here, or the transport delay. And the old ways, as I said before, will be modeling the system as an infinite dimensional system because of this continuous integrative equation, doing a continuous predictive control. And then we have to apply Lyapunov-Krasovsky's functionals to do analysis. But we know in practice, control signals are digital, often these days, and discrete. And that the integration done on a computer is also numerical, that's also discrete. So the more appropriate analysis will be a hybrid system analysis. So recall that we have this first order compensator for this gray part of the delay that we already designed. So what we want is at TI, we want to predict what is this, we have a sample at TI, we want to predict what is the state gonna be at TI prime. So we do a integration of our information in a round the cutoff fashion. So this round cut integration has this horizon big delta with a summation of delta C and delta S. And also H is the step size of the integration we're taking, and P is the order of the integration. For example, RK1 is roughly an orders method. RK4 is the more accurate fourth order method. And in general, the numerical predictive control MPC is just the first order compensator plugged in this predictive state of the future. A special case to this MPC is when you truncate everything to first order by taking, for example, letting H equals to big delta, you're taking one step integration over this entire range, and it becomes a first order approximation. So this term is very easy to compute compared to the general predictive formulation. Now we can do some hybrid stability on the system. Omitting the details, the bottom line is we'll have some nice term that we know that will make the system converge because of a nice controllers to it. But because we have prediction error, we're doing forward prediction. We also have sampling error during this discrete sampling stage. That's giving us some trouble. And we would like to bound these terms somehow. And overall, we can arrive at a rather complex expression that will determine by how big the sampling period is and how big the bound of your prediction error would be depending on the order and the step size you're choosing. Also the model, the error in the model you're using. So with this, let's call this control Lyapunov metric, if you will. Using this Lyapunov metric, we can actually get a sufficient condition on sampling type. So if you're sampling super fast, then your system can have some exponential stability under a certain rate of convergence. And then we want to analyze what is the computation time effect on the overall metric here. So at TI, we're trying to compensate for this jump here, except because we can use different order of the method and also step size, the delta C can change. And delta C would potentially affect the total delay. So we can express that by assuming some computation model on how long we can use to compute different prediction, different RK method, and arrive at a general form of the bound that we plug into the metric here. That sort of let us analyze how computation time would affect this Lyapunov metric. So let us do that on an example here. So the example we use is a double integrator, very simple linear dynamics, except now it has the delayed model added to it. And it's also tracking a variable frequency sinusoidal trajectory, making the entire system non-autonomous and nonlinear in the sense of time. So for this Lyapunov metric we just introduced, we like to plot it against computation delay delta C. And what we want to understand is how a computation time would affect the performance. So on the left graph here, each column is different increasing model error, and on each row is increasing system delays. As you can see, you would expect when there are very little errors and very little delays, it turns out you would favor higher order method over lower order methods, first of all. And you will favor compute longer, because longer computation give you better accuracy, and better accuracy give you better control, or in the sense of this metric here. So this is in the case when sample period is fixed at 0.1 seconds. You always update at 0.1 seconds, every 0.1 second of the control. While you're increasing delays and also the modeling error, it turns out this relationship will not hold anymore, as a lower order method, an RK1, or order method actually outperforms higher order method. And also it's not always good to compute longer, because longer computation can also lead to longer delay, and longer delay with bigger error, a bigger modeling error can give you worse control performance. On the other hand, if you somehow letting the sampling period equals to the computation delay, now we can update as soon as finish computation. And then you can see a relationship that reverses, in a sense that there sometimes exists an optimal computation time for a certain metric that we have here. It's not always, it's almost always beneficial if you can update faster instead of compute longer for better accuracy. So in this case, frequency of control actually helps you more than accuracy of the prediction. So that was just plotting against some theoretical bound, and we can do this in the simulation as well. So in simulation, we tracking trajectory, we plot the same computation against the root mean square error of the tracking. For both, the left side is the fixed sampling time, the right side is the variable sampling time. And you can see for fixed sampling time, you have RK4 outperform RK1, and that in some case, in the simple case, changing the amount of computation doesn't matter too much, because we have very fast computation on these systems. But however, when you change computation, when you change the sampling equal to the computation delay, it almost always beneficial to have a lower time in computations, so that your frequency would increase. So this is corroborated with the prior results we just shown. On the right graph, we show some comparison between baseline methods and our proposed methods. As you expect, our proposed, the full-blown NPC actually outperforms other methods in different lengths of system delays. What's surprising is that the first order truncation actually works as well with very little computation, up until some point, a significant delay where the first order approximation wouldn't hold anymore. And also what's interesting is with a baseline controller, when applied naively to delayed system, actually doesn't perform as well as a PD control. So when you don't consider delay, your nonlinear controller actually doesn't outperform PD control just because of the additional term on the derivative there. And similarly, we'll have the trend when we plot it against a different frequency of our trajectory. So the last plot we're showing here is to understand this first order truncated control and what is the main benefit, when can we use it. So when we combine the delay of both transport and first order time constant, and the vertical axis is the proportion of that total delay that is dynamic delay, the first order delay, if you will. So how do we read this graph is at lower total delay, it doesn't matter how do you model the delay. At lower delay, all you need is find the total time constant and then feed that into this truncated controller. So it doesn't matter where the source of the delay will come from, whether being dynamic or whether being transport. On higher delay values, if it's still from the sources from dynamic delay, then the truncated controller will still work pretty well, where transport delays will have issues being compensated by the first order truncation here. Now we applied that simple method, the truncated controller to quarter order system, as we first have shown an example. On this smaller drone, the general delay is on a scale of 100 milliseconds. The augmented controller is simply using our nonlinear one, do a numerical derivative and multiply by some time constant that we can tune. So this is a separate work we done on the newer swarm paper, which is using a neural network for swarm planning. But the underlying controller was using this delay compensation controller. So although we don't have actual separate comparison results, it turns out that because of the additional aerodynamic during the interaction, the delay becomes significant. And thus, without compensation, it doesn't even work in any of the trajectory tracking tasks. All right, so to summarize what we discussed, we just established why eVTOL fixed wing aircraft is better for the urban air mobility applications. We then move on to define a set of modules for the unified control architecture for fixed wing eVTOL. And we can enhance it with some adaptive method and physics-based modeling, and using some novel sensor that can measure airflow vectors. We have a design strategy that can optimize our rotor configurations so it's better against rotor failures. And then we propose method that when the dynamics is partially or fully represented by DNN, how do we design and train controllers to it? And in the end, we have augmentations that can transform existing controllers for undelayed system into controllers that can just compensate for dynamic and transport delays that works on practical digital control systems. So with that, this work is supported and supervised by my committee, Joel, Sunjo, Richard, and Yisan. All the work, collaborative work are listed here if you're interested. And with that, I conclude my talk and I'll take any questions.